Greetings. Welcome to the NPTEL course on microsensors, implantable devices, and rodent surgeries for biomedical applications. I am Kaushik, and I will be taking you through the development and design of an electronic system for the stimulation and acquisition of the brain signals, acquisition of the brain signals and stimulation of the brain for rodent-based models. And this is the second part of a three part lectures, and in this we will be looking at how we can design a complete circuit that can achieve this goal that we have set. If you have not watched the first lecture, I will give you a brief summary on what we have done in the first lecture, which is taking us through the design considerations for developing the system, and in that we have seen what is the objective of a system, which was to stimulate and acquire brain potentials, biopotentials from rodents, which means that the system has to have a very small footprint and it also has to be wireless, and it also has to be battery powered. These are the considerations that we had when developing the system, and to achieve this we looked at several possibilities, whether in using development boards or in using ICs or ASICs, application specific ICs, to develop our own board. And at the end we arrived at this specific ASIC RHS-2116, which can stimulate and acquire biopotentials, either stimulate or acquire in any of the channels, and they have 16 channels in total. Now we will look at the circuit design on how we will interface this RHS-2116. Just this chip won't do the entire process that we need. We need several controllers to acquire the signals and convert it into useful information for the user, and we will be looking at how to interface that in this course, in this lecture exactly, in circuit design. First I will take you through how do we go about designing it, and how do we make a prototype for the system, and how to interface those components together. First, as I told you in the previous lecture, the RHS-2116 has its own inbuilt modules that helps it to acquire the weak potentials of the brain. Biopotentials are usually in the range of few 100 microvolts to millivolts. So even though there are multiple ADCs, analog to digital converters, that are available in the market, which can just acquire the analog signals, we need pre-amplifier stages to amplify these into readable signals for the machine when we convert it into digital signals. And these need stages such as amplifiers inbuilt or externally. If we have the stages externally, it will increase the size of the system, but in this Intentec chip you can see that it is inbuilt, and this is what makes this ASIC so cool, because we have a very small feature size. As a result of that, you can see this comparison with respect to the US currency placed nearby. This is very key for a system, since we are also working with rodent based models, and I want to take you through the overall structure so that you can get an idea of how these biopotentials are acquired. As you can see, this contains 16 electrodes from 0 to 15, which are connected to the sensors that are implanted on the brain, and these sensors will acquire the signals through these AC coupled high gain amplifiers that are placed here. These high gain amplifiers are specific for acquiring the biopotentials. You can see that each of these electrode contain a AC coupled high gain amplifier and a DC coupled low gain amplifier, and there is also a current stimulator selector here. This is used to select whether the particular electrode will stimulate or acquire at a time. When we put it in acquisition mode, there is no current passing through the electrode. In turn, the biopotentials are acquired through the AC high gain amplifier, and it is in reference with the reference electrode placed here. So what happens is that the biopotential get subtracted with the reference electrode or compared with the reference electrode in order to remove the common mode noise present in the signal. In very low ranges such as microvolts to millivolt, there is a huge noise associated with it, and we need this reference electrode to remove the noise. And when we put it in a constant current stimulation mode, which can do biphasic stimulation, this DC low gain amplifier, which is in reference with the common ground, will tell you the electrode potential due to stimulation. While the AC, I will repeat, while the AC high gain amplifier gives you the electrode potentials due to local field potentials and action potential, this DC low gain amplifier will give you the electrode potential due to stimulation. Now, in any stimulation setup, there is a common criteria that the charge neutrality has to be maintained, and you can see a charge recovery chip switch, which can be used to ground the excess charge that is present in the electrode. Now, this action is repeated for all the 16 electrodes simultaneously using the analog multiplexer. It switches between each electrodes very fast so that it appears to happen parallelly. Now, the constant current that is supplied for stimulation varies in the range of nanoamperes to microamperes, and the stimulation voltage is based on the bias that is applied in the Vstim plus and Vstim minus here. So, this is the inbuilt stages that are inside the RSS 2116, and we will try to interface it with other components to achieve a complete system. As you can see here, there is already a simple schematic provided in the data sheet. You can connect it via SPI lines with a CPU, microcontroller or FPGA. CPUs are otherwise also known as microprocessors when used standalone. So, we can try working around with that. Now, let us build step by step on how we will control the RSS 2116 chip based on the information that we have so far. So, in here you can see that the CPU or microcontroller FPGA can be connected, and initially I want to go about selecting microcontrollers. The reason for this is microcontrollers are generally cost effective and they are readily available in the market. You can procure one immediately if you want to, and they have a decent feature size as well. When you use only the chip instead of the development boards, microcontrollers are pretty small, and I am going to connect them via SPI to my RSS 2116. Now, you can see that this is a very simple schematic, and this requires a lot of back-end development such as programming using either embedded C or Circuit Python, but I just want to give an overview to the viewers on how design can be made, and I encourage you all to look into how a development board works, or how programming can be done to a development board, which you can extrapolate to this integrated circuit as well. Now, this SPI lines, which means serial peripheral interface, is a mode of communication, and usually they have 4 lines, 2 data lines, 1 clock line and 1 select line. The 2 data lines offer one-way communication from and to the microcontroller, that is why hence the 2 data lines, and the single clock line maintains the synchronous activity between the microcontroller and the peripheral. In this case our peripheral will be the RHS2116, and the select line will be used in case multiple devices are connected to the same bus. You can connect the same data line and clock line to multiple devices by using multiple select lines. Or in our case we are just using one peripheral, so we will just use the default address for the select lines. And the data lines will have designations such as master in, slave out, or master out, slave in. In this case we have D out, D in, serial data out, serial data in, data out, data in. These are just alternate terms for the same data lines, and these will be connected to the alternate line, which what does it mean? The data out will be connected to the data in of the peripheral and vice versa. And the clock lines are connected together, and the select lines, sometimes known as chip select, are also connected together. Once we connect this, we can notice that there are multiple lines present for the same terms in the chip. This is because RHS2116 provides low voltage differential signaling SPI. What does it mean? Low voltage differential signaling is a term to transfer data at high speeds with a low power, as it is evident by the name. And with differential we can understand that each line has its two counterparts, the positive counterpart and the negative counterpart, which act simultaneously. By this way we can send data rates with very low power and still comprehend the signals at the other end. We just have to use specific comparators that can differentiate the signals. So each line will have its counterparts. So there are totally 8 set of lines which will be connected to the 8 lines on the peripherals. And in this I will go ahead with selecting differential signaling, since that will make it even more better. So we are going to connect with LVDS SPI. This makes it much more faster and better, but note that some microcontrollers do not support LVDS SPI. Also, we have also noticed that in the data sheet the RHS2116 has a capability to send 40 kilo samples per second, and when translated to 16 channels, this is 40 kilo samples per second per channel. When translated to 16 channels, we have a massive samples per second that arrive from the biopotential acquisition chip. And the overall speed requirement when we take a 16-bit ADC, it will be around 10.24 megabits per second. And microcontrollers and microprocessors usually have an upper limit of 2 megabits per second. If you overclock it, maybe to 6 to 10 megabits per second. But it's very rare, and the microprocessors are extremely costly. And in this case, this is where FPGA comes into play. FPGA is field programmable gate array. It's a very popular term, and as it suggests, it can be programmed and reprogrammed as many times as you want. After production, it contains an array of logic blocks which can be programmed to perform digital functions, and the specific properties of FPGA is shines through when you need flexibility in your device or high data sampling rates. FPGA can do this. This makes it essential for brain acquisition, because brain signal acquisition, because we are going to be taking signals at a very high sampling rate, because neuro potentials acquire at a frequency of around it's a huge range, 1 to 10 kilohertz. This is not just neuro potentials, it is also including other local field potentials and EEG signals. And we need to be able to pick up all those signals, and we need a high sampling rate for that. Now, because of this, I will be alternating the microcontroller with the FPGA. The reason I went with microcontroller and microprocessor in the initial stages is because most of you might be comfortable with working using a microcontroller, and in rare cases microprocessors, and the cost is also very cheap that is associated with them. But FPGAs, when you need a system that can be used for neurosurgical applications, you cannot compromise on data rates. So we will have to go with FPGA, and we will be using LVDS SPI to communicate with our Intentec chip, the RHS-2116. Now that we have decided that we are going to go with the FPGA, there is also one more step involved in it. FPGA usually is programmed using Verilog codes, and you have to control the stimulation or acquisition electrodes that you are going to work with in real time, and you have to give the stimulation parameters as well in real time and acquire the signals in real time. All these things will be a bit of an hassle to work with just the FPGA. To make our lives a little bit simpler, we can interface this with another microcontroller that can help us translate the signals coming from it and provide the FPGA with real-time programmability. Now this is a circuit that we can work with, and we will be moving forward with working with this kind of circuit. As you can see here, I want to show you this register file which is used for controlling the amplification and stimulation, and this will be in turn controlled using the SPI interface digital controller. Now that we have established this circuit of ours, we will be using a microcontroller which will communicate using SPI or differential SPI with our FPGA. This will communicate with our RHS-2116. Now we need something that can communicate with the GUI. Since we are making it battery powered, we need to make it wireless as well in communication. So we can connect it with a battery module for powering it, and this will also provide power for our FPGA, and for stimulating the brain we can use the same power as well. Note that this is a very simple representation in general, and we will be needing a lot of regulators in between to regulate it, lots of protection circuit, but I am not going into details since I want to give you an overview of what is happening. And for communicating to the GUI, we will be using either the Wi-Fi modules that are available or BLE modules. There are lots of BLE antennas available. We can use the antennas with the correct specifications, or we can directly use the modules that are available, which has a significantly small form factor, so that our device in overall would not be too big. And let's frame the overall schematic with whatever we have so far in our hand, and we'll try to frame an idea of how the schematic should be. So there is our microcontroller, which will be communicating via SPI with our FPGA. Then the reason for using SPI between the microcontroller and FPGA is FPGA usually is communicated with SPI, and it's pretty fast to communicate using that. You can use other modes of communication such as UART or I2C or I2C communications as well. But SPI is pretty established since we are already using LVDS SPI here. I am using the same there. Then we have the stimulation acquisition chip. Now there will be 16 electrodes here, which will go to the sensors that you will be learning about, and those sensors will be implanted in our brain, in the rodent's brain. So now that we have interfaced it with the sensor, we have to send the data from the microcontroller to the GUI. So let's include our BLE module as well here. We can choose Wi-Fi or BLE modules. So I'll be going with the BLE module, and I'll explain to you why later on. And this will communicate with our GUI here. And so far we have the overall schematic that we need in order to make a system that can achieve our objectives. And this is the overall system that I had drawn beforehand. So in this you can see that there are detailed descriptions of whatever we have drawn in the previous slide. So this represents our sensors that will be implanted in the rodent brain. This will either send signals, and the RHS-2116 will acquire from this, or stimulate the electrodes. And stimulation can be done either to the surface electrodes or deep brain electrodes. Both of these electrodes will be discussed in the lecture by Professor Hadik, and this signal that we have acquired will be transmitted to the FPGA, and the FPGA will be able to handle the high sampling rate of the RHS-2116. And once we get it from the FPGA, we will transfer it to the microcontroller, and the microcontroller's only job will be to transmit it to the GUI or change the stimulation patterns. And this everything will be biased by the battery, so we have to choose a suitable battery with a small form factor as well. So the battery has to be small, it has to be rechargeable. So let me consider a lithium polymer battery, which is widely available, easily available, and comparatively cheap. Usual batteries come with 3.3 to 3.7 volts, and we can vary the size, and the charge capacity varies according to that. And we can supply all the microcontrollers. This battery will be supplying our positive stimulation supply and the supply for biasing. For biasing, we will need to bias the microcontroller, we will need to bias the FPGA, we will need to bias the RHS-2116 for the amplifications. For acquisition also we need to bias it, and we will find the common voltage across this and try to use the same regulator with the capabilities that can power all these chips in a single regulator and use those regulator. This will reduce the form factors since we need to use minimal number of chips. Also we can boost the voltages as required. Some microcontrollers work on 5 volts, some microcontrollers work on 3.3 volts logic levels, and we can boost or buck the voltage levels accordingly. We can use charge pumps or boost regulators, but I would prefer charge pumps since they do not use inductors for boosting the voltage levels. For our stimulation purposes, we need to use a separate stimulation supply as per our needs, or if they match the regulators supply voltage, we can use the regulators as well for stimulation. And for negative stimulation supply, we may need to use inverters for inverting this supply and using them for stimulation purposes. This will be for stimulation, this will be for biasing the microcontroller, FPGA and the RHS-2116. Also, since we are using BLE, beforehand we need to program the microcontrollers so that it can in turn program the FPGA to work according to the user's needs. In order to program the microcontroller, it will be easier via UART communication. UART stands for Universal Asynchronous Receive Transmit. You can remember that any synchronous communication will have a clock signal, and asynchronous signal won't have a clock signal. And in this case also it has only 2 lines for transmission and reception. In this also it has only 2 lines, one for transmission and reception. In USB to UART interface, we will convert the UART from the microcontroller, the UART lines, into our standard USB format, which can be connected wired to the GUI. This way we can debug beforehand, also program according to our needs, debug, once we connect it wired to the GUI, we can program it wired or debug it before yeah. Once we receive the UART communication from the microcontroller, this USB to UART interface converts it from UART to a standard USB format, which can be transmitted or received from the GUI, and this can be used to program the microcontroller according to our needs or debug it beforehand before we fix the parameters so as to establish communication properly. Also, since the amplitudes of our signals from the brain are extremely small, and we are using, even though we are using low voltage differential signaling, which reduces common mode noise in the signal lines, there may be static discharges that may accumulate on the lines, and this can be removed, and the lines can be protected using a dedicated electrostatic discharge chips. This discharge lines use reverse biased diodes to discharge the opposite charges to the ground, and these will be tapped from the lines directly. This electrostatic discharge will tap into the lines of the SPI and it will ground them from electrostatic discharge. So, this I hope would have given you an overall view for the schematic. I did not go into the details of what microcontroller we will be using, what BLE or Wi-Fi module we will be using. There are tons of options available which we may need to look over the internet. There are tons of options available for FPGA chips, but what I most wanted to stress on is the biopotential acquisition and stimulation chips, which may be useful for these biomedical applications, and these can be configured in any format that you want. This is one of the formats that you can use to tap into this potential of the chip, but there are other formats that can be as effective or even more effective than this circuit. So, that is the goal of this, and let us summarize what we have seen so far in this module. We have seen the RSS 2116 chip in detail, the internal structures of the application specific integrated chip, how the pre-amplifier stages are present inside it, how they amplify the biopotentials as well as read the electrode potential due to stimulation, and the stages involved for signal acquisition stimulation, which are again the amplifiers. Plus we saw how charge neutrality is maintained with the help of the charge recovery chip, charge recovery switch. Then we saw about how we can interface this chip with our microcontrollers or FPGAs in order to make it a complete system, and how we can control it, how it makes it easy to control the system to achieve the goal that we want. And we also saw the overall schematic, how the components are all interfaced together. Even though this is basic, I will encourage you to look into the details of the how each component can be connected with one another. Any basic interfacing will have power lines associated with it and data lines associated with it, and this is where it gets complicated at times, but believe me, this is as simple as it gets, and I will encourage you to look into the details of how an interfacing can be done to any chip in general. In the next module, we will look at how we can translate the schematic that we have done into a PCB design, how we can do a schematic of the exact circuit that we have done. This is an example of a schematic that is done using Altium Designer. This is also from Altium. This is a PCB layout which translates this schematic into PCB layout, which can be printed and manufactured using a Gerber file, and I will take you through the steps on how you can make your own schematic, how you can generate your PCB layout and generate a Gerber file so that you can print your own PCBs with the help of these softwares. These are called electronic design automation softwares or CAD softwares, computer aided design, and these are some of the softwares that are popular. ECEDA is a free software and it is web based. KiteCAD is also free and open source, whereas Altium, OrCAD and Eagle OrCAD is from Cadence and Eagle is from Autodesk. These are licensed softwares. I would encourage you to start with EasyEDA or KiCad to learn how PCB design works in general. It will be useful not only for biomedical applications but also for any circuit that you may have to or you may want to design. And this I keep putting this picture to stress on the fact that we will be ending our system design on a PCB, and to reduce the form factor as much as possible for rodent based applications. And if you have any doubts regarding this lecture, feel free to reach us out on the forum. We will do our best to answer your questions, and I will see you in the next lecture. Thank you.